Let me write this thing. Define problem, solving question, whatever. There should be some. This should be some. Huh. Okay. So let's start. So let's quickly recall what we done in this week and then go to problems. Mm, help me recalling what we have done in this week. So let's start. Recall. A quick recall of what we have done. Then we'll do the problem as usual. So we started with what? In first lecture of this week, we defined what? System of distinct representatives, right?
Yes.
What is that?
So, if we have a set with some elements, we pick. We have a collection of sets. Then we pick for each set a
An element from
representative
that set.
element.
Yes, from that set, and for each set we choose a different element. Okay, so then things goes to what? There is one theorem which is called Hall's theorem, which is basically necessary and sufficient condition. Basically, what is this SDR is saying basically? Okay, so uh, so if we have suppose A1, A2, AN sets and A1, A2, AN sets, then this says this basically to have distinct representative, we should have this condition hold na, that okay, let's say this thing is sets are running over an indexing set J as notation. I'm running AJ J belongs to capital J. Then this thing should hold if the SDR exists. Then this thing should hold that union of J belongs to J AJ. Union of J belongs to J. J belongs to J. Cardinality of AJ should be greater than cardinality of J. This thing should hold, but Hall's theorem, says that this condition is necessary and sufficient. So there is one theorem called Hall's theorem. So what is the statement of Hall's theorem?
For some bipartite graph, right, we have a matching from the bipartite set
Ha,
X to Y, if and only if the neighborhood of cardinality of the
of
neighborhood of
neighborhood
any
of X
subset is greater
is
than the cardinality of the subset itself, greater
yes,
than or equal to.
yes, that's correct. So this is Hall's theorem. So what is the, and we also define for this Hall's theorem we need some term called matching. What is the matching? Definition of matching?
Matching is an basically is an matching is an set of pairwise disjoint
Set of pair,
set of
right? That's
set of
yeah,
pairwise.
set of pairwise disjoint is. Then we define what? Vertex cover.
Yes.
What is the vertex cover?
So it's
Sub,
a set of vertices that
yes,
such that all the incident edges are basically
yes,
covered by it. You
yes,
have no missing edge.
yes. So this is vertex cover. Then using Menger's theorem, uh, we see some correspondences in lectures. Basically, okay, in the proof of Koning's theorem, all these things I guess used. Then we see Koning's theorem, right, which used in proof of Gauss theorem. Koning's theorem. So what is this?
The maximum size of a matching of a bipartite graph, which was equal to the minimum cardinality of the vertex cover.
Yes. So this is maximum size of a matching in a bipartite graph. G is equal to the minimum cardinality of the vertex cover, right? So in this proof, I guess we use this Menger's theorem of this. And then what we did, we defined planar graphs. Uh, then for planar graphs, we have Euler identity. What is planar graph?
it's a graph that is that can be embedded on a surface to distinct points. Uh, so no,
Yes.
we can embed it in such a way that each point is distinct vertices and edges, no overlap.
Such that edges does not intersect, right?
Yeah.
And then we define plane graph, which is planar graph together with an embedding in
Yes.
plane. Then we define Euler, what is Euler identity?
So it was that the cardinality of the set of vertices and the added with the cardinality of the set of regions is equal to the cardinality of the set of edges plus 2.
So V minus E plus F equals to 2, right? For
Yes.
what graphs you have written this?
So basically connected plane graphs.
E is connected plane graph. So this is your Euler's identity for planar graphs. So you can find its analogs are there if you have done some topology course. So this is basically what call characteristic number, something like some term like that. So V minus E plus F, here it is going up to only 2 dimensions. If you go higher dimension, then this is basically alternating sum. And in fact, this is a rank of 0-dimensional cohomologies of a space. So if you have done this course, then it may relevant. Otherwise, you can skip this comment. And then what? Then we define what? Then the problem arises how to say a graph is not planar. If it is planar, we need to give a embedding. But how to say it is not planar? Then we found a theorem which is interesting. But whether it is strict or not, that we will see. So G be a planar graph. Let G be a planar. Connected, I guess, also need. Does this need connected graph? Where we prove A set cardinality should be less than 3n minus 6?
Less than 3n minus 6.
Yes, the theorem which in class in which we proved that cardinality of E should be less than 3n minus 6.
It was just in a planar graph.
Okay, need not be connected, right? Okay. I guess in this proof we use this theorem, na, Euler's identity. For that we need, okay, that we can generalize for not connected as well. Okay, I will do that not connected generalization. Okay, fine. So on n greater than 3 vertices, then okay, cardinality of E should be less than 3n minus 6. This theorem is saying basically if G is a planar graph on n greater than 3 vertices, then cardinality of edges should be less than 3n minus 6. So this says that if some have more edges than this thing, then on given vertices, then this graph is not going to be planar. But what about, is this boundary strict? Can we make it something lower? So have you thought about this?
Yes, it can be made lower. But, so this is basically a bound, but we can definitely, I think, get.
No, I will give you a planar graph which has exactly this many edges. Okay, in this lecture I will do this. For each n, I will give you a planar graph such that it has exactly 3n minus 6 edges. So you can't expect to modify this result for lesser than this bound.
No, this what I meant to say is this is a bound, right? Not equal.
This is a bound. I am saying, is this bound strict? Can you make it slightly lesser, like 3n minus 5, something like that?
No, no. In general,
You can't make.
Yeah.
Yes, you can't make. For a specific kind of graph, you can make it.
Yeah.
Like for bipartite graph, you have some bound. So, what is for bipartite graph? Planar bipartite graph, we also have a bound, I guess. That is planar bipartite graph has at most two n minus 4 edges on n vertices. Okay, so let's go to problem with this. What we also did this, na? Maybe you followed last lecture this 4 coloring thing.
4 coloring theorem.
Yes. What is that method called? Discharging method, something like that.
Yeah, the discharging effect.
So in this, in that he what the theorem states basically, which he said proof is quite harder and proved by computer calculation. It says that any planar graph can be colored by four colors, right? Vertices of any planar graph. That's the theorem, right?
Yeah, any planar graph can be properly colored with the
Huh.
vertices can be properly colored with.
So for four it is quite hard to prove, as he mentioned in lecture. But in this problem solving session, I at least we can prove for five. At least any planar graph can be colored by five. So we will see that proof. Okay. Huh. So we have discharging method. For five it is easy, but to reduce it to four, it may be harder. I haven't followed the proof, whatever paper he suggested. So this is the recall of theory. So let's go to problem. Huh. So this is theorem. State and prove Euler's formulas for a planar graph with k components. Hmm. Can you think something or suggest? Like for connected graphs, we have this thing, na, v minus e plus f equals to. So can you think something for higher, something for this k components? Suppose graph is v comma e, and this is union of v1 comma e1 union v2 comma e2 union so on vk. How many components you said? K component vk comma ek. Now can you say what is the formula of vertices in G minus edges in G plus faces in G? What is this thing? This is the Euler formula, right? That we need to find out. Can you hear me?
Yes.
So can you say something? Vertices of G is what summation of vertices of Vi, right?
Uh,
So this is summation vertices of Vi. And what about edges? Edges are also there. Edges in Ei basically. Edges in this Vi comma Ei are the only edges in G. What about faces? V minus E, sorry. What about faces? Is it also sum or something more or something less? Ah, you can't say, or like suppose you have this thing. This is suppose this is a graph G. This is V1 comma E1. This is V2 comma E2. So what can you say about faces? This graph have two faces. This graph have only one faces, right?
yes.
So can you say something now? How many faces this has, which is union of k components? Is the faces is sum or something lesser or something more? This
Uh,
graph this graph have two faces, na, one and two,
yes.
and
One
this graph has
face.
only one faces. So how many faces this G have? Sorry, this graph G have, which is union of these two.
Okay, so we have to reduce one common faces for each of the components, basically.
Okay, so how much we have to? Okay, so what I have to do?
So first we sum the faces,
Huh?
then we basically take out uh, exactly k minus one faces.
Yes, correct. But what is this? This is summation. You can say summation common. Vi minus Ei plus Fi minus K plus 1. But what is this? V minus E plus F. This is 2.
Two.
So this is 2K minus K plus 1. So this is K plus 1. So this is your Euler's formula for K connected components, right? Is it clear?
Yes.
Okay. This is also done in problem or given as an exercise in class, something like that. Given as exercise, right?
I haven't gone through all the lectures actually.
Okay, okay, fine. So, are you able to follow this, or I should go
Yes,
somewhere again?
I'm able, I actually did try to at least go through some of the main topics through the slides before joining. So I suppose I can understand this bit.
Okay. So, okay, wherever you don't understand, tell me. I will recall the
Okay.
theory at that point. Okay. So, so this is second problem. Prove that every planar graph isomorphic to its dual has exactly 2n minus 2 edges. So, have you understood the problem? What he's asking? Do you
What
know
is
this?
the dual?
Okay. So, I should explain you dual. So, given a graph G, so how to find its dual? Dual means that corresponding to each face, you are putting a vertex. I should write.
Okay, yes. Yeah,
Are you able to
I
recall?
remember. It was in the Königsberg bridge problem.
Yes. So for each face, you are going to put a vertex. Then between these two vertices, you are putting an edge. If these faces are separated by an edge, something, and then same, right?
Yeah.
So, and when self loop, this basically if the both side of the an edge are basically, when this there is a self loop on a face, basically when both side of a edge is the same face, then there is a self loop on that vertex corresponding to that face, right?
Can you show a example of self
Huh,
part?
huh. So suppose you have something graph like this, uh, something like this, or something like this. You have, these are vertices v1, v2, v3, v4, v5. You are these vertices. So this is your graph G. You are going to find its dual. So corresponding, how many faces we have? This is F1, this is F2, this is F3, and outside face is F4, right?
Yes.
So we have four faces, 1, 2, 3, and 4. Now each face is what? Each face is connected, like each face is separated from another bounded. Each face is, each bounded face is separated from this unbounded face by an edge. So
Mm.
there is a edge joining to this. This is my vertex corresponding to F1. This is my vertex corresponding to F2. This is vertex corresponding to F3. This is vertex corresponding to F4. So corresponding to, there will be an edge from each vertex to F4 because F4 is
Yes.
separated from each of these faces by an edge.
Yes.
So this thing. Now, now there is going to be no self loop because inside and outside of the each edge there is a different face basically. If you go inside of this edge, there is a face F1, outside of this edge is a F4. inside of this edge is a f2, outside of this is a edge is a f4, inside of this edge is a f3, outside of this edge is a f4. So there is going to be no self loop. Now f1 and f2 are going to be connected by an edge, and f2 and f3 are also going to be connected by an edge. So this is going to be its dual, right? Are you able to follow or not?
Yes. I was just asking when the safe loop occurs.
Something like this graph.
Okay, so it will have only just one vertex, not with many vertices.
Yes, it have only one vertex and a self loop.
Maybe okay, so if you can we have
Because
this with
both side
multiple
of the edges
vertices?
have same face, right?
Can we have this with multiple vertices in the dual?
Yes, we can have.
So I mean exactly that. Say we have an edge, and that edge one of the endpoints of the edge has a self
Yes,
loop.
we can have, right? So let me think what kind of graph we have to draw. So we need both sides of the edges should have same face. So just extend this graph, no? So you have these vertices, and then something. Uh, so then what you can do something like some triangle here. So for this graph, if you go to, yes, if you draw this unbounded face here is a self loop as well, right? In this one, how its dual will look like. Its dual will be one unbounded face, one bounded face, and bounded face and unbounded face is joined, and on this unbounded face there is a self loop,
Okay.
right?
So here, so the only thing matters is that if the
Both side have same face.
both sides, okay, okay, yes, I got it. Both sides have the same movement. Okay.
Yes. Okay. So can you think now for problems? I guess this should be easy.
Okay.
Prove that every planar graph isomorphic to its dual has exactly 2n minus 2 edges. Can you see?
2n minus 2. Okay, so this comes from the bound that we put on the planar graph before, so the 3n minus 6.
Okay. So you want to say a cardinality of edges is less than 3n minus 6? Then what?
Okay, no, that was the 3n minus 6. Let's say. So we have this many edges. Mm,
Think about Euler's formula. What is this dual graph can give you? Think about this thing first. What this dual graph is saying to you? Dual are isomorphic, and they are isomorphic. That means what? If the graph is isomorphic to its dual, that means what? If
Oh,
two
so
things
every
are,
graph has
yes, yes,
so yeah, so they have so here we have that n is equal to the number of regions.
yes. So number of vertices should be same as number of faces, right?
Yes, yes. So yeah,
Yes.
so
That means
in yes, that directly gives
yes,
the result we see.
yes. Huh. So that is basically V minus E plus F equals to. So then, so E is equals to V plus F minus 2. So that is 2n minus 2. Cardinality, I should write. This should be cardinality. So next problem, this is easy one. You know outplanar graph?
What?
Okay, let me define. A graph is outplanar if there exists an embedding of the graph on plane such that every vertex of the graph lie on the boundary of its unbounded face. This is the definition of outplanar graph. You can see. So a graph is outplanar if there exists an embedding of the graph on plane such that every vertex of the graph lies on the boundary of its unbounded face. So what is the problem? So the problem is question prove that every uh before this I should prove this thing, right? Outplanar, let's prove this after this. Let's prove first this. Prove that every planar graph has a vertex of degree at most 5. Can you see this? This should be easy. The another one should be harder if the outplanar condition is given.
I agree. And also what is it?
Degree at most 5. Mhm.
This is not obvious to me. So so I can see this for the outplanar graph, but not for just planar graphs.
No. Outplanar for this will be more strict result. Like at most 5 will be replaced by some smaller number. I just need planar for planar graph.
So is this a planar graph? Consider a point, a vertex surrounded by say 2, 3, 6 vertices, and then just
Okay.
join each of them to the main vertex inside.
Two main vertex means?
The first vertex that is placed on the center, and then
Okay.
around this.
Okay, so you are saying let's say this vertex has degree 6.
Yeah.
So then you are saying there are some vertices, 6 vertices which are joined to this. So then what?
So this is a planar graph.
Okay. So what?
So we have a vertex with degree with 6, no?
So, but we
So
have a vertex with degree 5, right? Degree 1, at most 5 even. Even we have this many vertices of degree.
okay. Sorry, I misread it. Yeah, at most 5. I was focusing on the yeah.
I'm
Yeah.
not saying all the vertices. I'm
Yes,
saying
yes,
there
yes.
is a vertex.
Yeah. I, uh, I understand now.
Okay. So can you think something? Think about this thing. Now you have this bound for ages, which you have proven in class for planar graph. The number of edges should be less than 3 and minus 6.
Oh, so then we have.
Suppose you have more than, suppose you have a, every vertex has degree greater than what? 5. So at least, so every vertex has degree greater than 6, right? Greater than equal 6. So what you can say, you have given degree of each vertex vi is greater than equal 6 for all I. Now what is the connection between edges and vertices?
So we have that sum of the vertices
Sum of
is,
degree of vertices,
yes, sum of degree of vertices
hmm,
equals to
equals to,
twice of h, the cardinality of h.
right. So what is this? Left hand side.
So
This
this is
thing.
at least okay. So six. So this is 6n,
Huh?
at least 6n. Then we have
Hmm.
okay on 3. Then the edges becomes at least 3n.
Huh. So cardinality of edges should be bigger than equals 3n, but this is what? This is strictly bigger than what?
Uh,
3.
3n.
So that is not possible, right? So that
Yes.
means G is not planar.
Yeah.
So this will imply there exists a vertex in planar graph of degree at most 5. So can you produce same bound for bipartite graph? That will be more nicer, right? In this case, the boundary is, there is a vertex of degree at most 5, you are saying. But can you produce something for bipartite graph?
So for bipartite graphs, we have that the degree of edges is not more than 2n minus 4.
Hmm.
So that we found then 2n minus 4 is equal to.
Degree of vertices. I guess for that I can't think an immediate argument. Can you think something?
I'm trying.
I'm also trying. I haven't thought about this problem. So let's think together. Mm, so when this thing holds, then what we can say? This thing will always hold. Now, summation degree Vi is 2 times cardinality.
Is
This will hold for bipartite as well, because mm, 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 mm. Vertices have degree 1. You have 2 vertices, you have 2 vertices here. Degree of vertices. Sounds good. Good. Okay, so let's write and we will get, I guess, summation degree of Vi is equals to 2 times cardinality E, this degree of Vi, and this is bigger than, mm, this showing should be less than 2n minus 4, and left hand side, if each vertices have degree 4, then this left hand side is this, each vertices have degree 4, then this left hand side is 4n. So this is saying you that cardinality of E is, and if each vertices have degree, if each vertex have degree 4, have degree greater than 4, so that means this will say that cardinality of E is what? This is bigger than, cardinality of E is less than, mm, incorrect. Degree of Vi is greater than, sorry.
the
This will,
cardinality.
uh, cardinality of E should be bigger than equals 2n, and which should be less than 2n minus 4. So yes, for bipartite graph, this will be 3. There exists a vertex of degree at most 3. So this is also good. So are you able to follow, or I should write?
Yes.
Let
Is
let
this is there a relation with the Kuratowski's theorem with the K33?
with
So
that.
when so the planar the non-planar graphs in, in the Kuratowski's theorem where we have that if there's a subdivision with K5 or K33,
Huh?
then it's not planar.
Yes, for not planar, we'll see. What graph we see that K5 is not planar, right?
So no, I was saying that this is the so maybe we can think about this with in that perspective that when you have that K33 with degree 3, so then each
Okay.
vertex has degree 3, right? So then
Huh?
we have that it's not planar anymore. So then
Yes.
that is confirmed here. Huh?
Yes. That is confirmed here as well, right? No, that is not confirmed here. That is not confirmed here from here, because this is saying that there exists a vertex of degree at most 3. So there all vertexes are of degree 3. So this is not confirming from here, right?
Okay,
Hmm?
okay. Yes.
But from here, can you see what about KMN? Okay, I should remark it later. What about when KMN is planar?
Uh, uh, can you repeat what you just said?
When this KMN is planar, basically you have in lectures you have proved this K33 is not planar, right?
Yeah.
So when this KMN is planar or not planar?
So we had that if in the
So this is another thing we have proved. I will tell it later, okay? If you can't see, if you can see, you can tell me. I will tell you. I will do that. Okay. So we have proved that any bipartite graph on n vertices has a vertex of degree at most 3. Good. So next problem. So okay, we are going to talk about our outplanar graph, right? I defined outplanar graph. Okay. So now we need to show the bound for outplanar graphs. Question: prove that every outplanar graph has a vertex of degree at most 2. So do I need to write the proof of this black colored statement? Are you able to follow that? What I written, or should I write it? Proof this bipartite graph.
yes, yes.
Do I need to write, or
No,
is it okay? Fine. So let's go to this problem. Every outplanar graph has a vertex of degree at most 2. This is interesting. This is like saying something closer through tree basically. In tree, we say that there is a vertex of degree 1, but this is something closer to that of degree 2.
mm. Oh, yes.
The specific thing is that this is outplanar basically. So how you will use that? outplaner is saying that this unbounded face is boundary to each vertex. So that means what?
So no, so no two vertices are connected, have an edge such that some other edge comes under it.
What do you mean by that?
So so if two so we need at least
Okay,
four
you
vertices
are
for
saying
this,
this kind
suppose.
of figure cannot. Okay, you are saying this thing will not going to happen basically. No
No,
vertex
so
come.
K, so suppose regular K, four regular graph will not happen. So we need to remove at least one edge from it.
You are saying this only, na? This kind of cases is not possible.
Yes.
Okay. So so what?
So
So what?
I think if any graph has to
I
have.
guess we are talking about unbounded faces, so we should go. Better we go to dual now. So if you go to its dual, then what is going to happen basically?
For it. So then we will have uh, exact okay,
So you have this basically, na? Vertices corresponding to some bounded faces and a vertex corresponding to unbounded face, right? Some vertices
yeah,
corresponding to bounded faces. There
yeah.
will be some bounded faces, and this vertices is corresponding to unbounded faces. Now there will be have some edges, but the first claim is this thing. This will be a tree. Vertices in the
Okay.
graph induced on the vertices on the bounded faces. This will be a tree. Is this clear or not?
Mm, mm, One.
Huh. This is basically by outplanarity. So you should think in this direction. What happened? There cannot be a self loop, right? This is the thing we are saying. First, first argue that there cannot be any self loop on this bounded one. Why?
Well, that means then we can't have the bounded edges all connected, all adjacent to each other in a sense. So we can't have say uh, if we think in K4, then here what happens is that all the four edges are all the four so all the three, actually not four, three bounded regions, they are
Hmm.
adjacent to each other, so that creates the cycle, corresponds to the
Anyway,
cycle.
on on dual any bounded face, there is not going to be what I see, what I feel that this should be true. On dual graph, on vertices corresponding to bounded faces, there is not going to be any self loop. It can occur only for unbounded face. Is it? Does it seems clear to you? Or I feel this should be correct. Does it correct or not? Because this bounded face cannot be common to both side of the edge, right? Because that edge is bounding to that bounded face, so it cannot be common both inside and outside. Outside there will be some different face, so there cannot be a self loop on this bounded
So
one
I'm
corresponding.
thinking that okay, self loop is current. I was talking about the cycles. So the
Okay, you are talking about cycle, so I argued for self loop. There will be not going to self loop on these bounded faces. So
yeah,
okay.
that is okay. I
Okay.
was previously with the K4. I was saying that
Okay,
yes,
you are talking about cycles. Okay, tell me.
yeah.
हाँ, बोलो.
So there will be no cycles either, because when we have the regions all adjacent to each other, then that
हाँ.
creates the that violates the outlinearity of the graph, and that
How?
exactly corresponds.
How
If
how
you
how
have
it violates? हाँ.
for example, if you take the K4, see that
Complete graph on four vertices.
yes,
हाँ.
draw it as
Okay.
a pen. plane graph.
Yes. Okay. So this is,
So
bolo.
So this corresponds to the cycle in the bounded part of our graph above, because yes, as a cycle, because see, all the bounded regions are adjacent to each other. So the left hand side bounded region is adjacent to bottom one and the right one, and similarly for all the others. So that creates a loop in the unbounded part of the dual, bounded part of the dual.
Hmm.
So then, as we cannot have this type of K4 like graphs in our planar graphs to have
But how
it
you'll
be
argue for it precisely? What is actually what? Why this is actually not possible? You are using this thing. I got you. You are trying to get an intuition by using this, but how you will prove it precisely? Are you understanding what I am saying?
yes,
So how you will argue for it precisely by using definition or something like? What will happen if there is a cycle?
on the dual?
Yes. If in a bounded spaces there is a cycle, so then what will happen?
Then it must be that these three the vertices of the cycle correspond to regions such that these regions are adjacent to each other.
So that means the vertices lying between them. What will happen to that vertices? Uh, can we say something like that? Not exactly. I guess that will not give us something. So if this will happen, so what is outplanar? That means, there will be some vertex lying in between them, na? In that case, and that vertex is then not going to be boundary to this bounded face. Yes, we should write that. I guess then it will be much clearer. Consider the graph, subgraph of dual on bounded corresponding to bounded faces, corresponding to bounded faces, bounded faces. If there is a cycle, that will mean cycle. Let's say on, let's say V1, V2, V3, then again V1. This is our cycle. This will imply, this implies, this implies there are faces, there are faces, there are bounded faces, faces F1, F2, F3, which all are adjacent to each other. To each other.
We should better say that
So
F1 is adjacent to F2 and F2 is at, so for in general, because I don't think if we extend it further, then it is necessary that all of them should be adjacent to each other. Just that once uh, uh, if we write it as
if you go more than F3, then it will
yeah
not
yeah
correct. So yes, we should say that some uh, there will be a face which is adjacent to what?
to at least one and at most two. So if
This
there's
will
a
be
cycle, then there will be a face adjacent to three of at least three of the regions, right? Because say we have the first region adjacent to the
no.
second,
Huh?
then we go. So you can kind of imagine triangles one after another. connected to each other, right? So then what will
हाँ
happen? This one part of the triangle is connected, not adjacent. Yeah. Then right. So basically, you are drawing some squares and
हाँ
diagonals of the
हाँ
triangles, right?
हाँ हाँ हाँ
Yeah. So draw another square beside it, connect
okay
adjacent to it. So
okay
as yeah.
okay
Then put another diagonal in it.
okay
Uh, so uh, so you see that the T2 is connected to the one next to it, and then if we put to the top right vertices, if it goes to from the top right vertices to one to the bottom left, then
hmm
it becomes that at least one of them is connected adjacent to three of them.
okay. So if there is
So
a cycle,
at least
so
so basically my claim is that at least one of the regions will be adjacent to three other regions.
but this
If
is
there's a,
not correct, na? Well, okay, three you are including unbounded one also, na? Or only bounded one?
I think it will work even if we restrict it to only bounded ones.
But bounded one, it is not clear. Why? How you are saying this region is this adjacent to three region? One region is this region, one region is this region. This is
Yeah.
adjacent. So this is
So then
adjacent to only.
when you create a cycle, what
Huh?
happens is one of the vertices gets kind of covered with an edge, right?
Huh?
So that creates the extra
So,
bounded
so you
region.
are saying let's draw this dual. So this will be vertices corresponding to T1. This will be vertices corresponding to T2. This will be vertices corresponding to T3. This will be vertex corresponding to T4. Then you have edges between them. From T1 to T2 you have an edge. T2 to T3 you have an edge, and T3 to T4 you have an edge.
Yes.
Then what? Then
Then create a cycle
T4
on
T4
the
to T1 you don't have any edge, right?
yes.
Huh. So what?
So now you create a cycle on the dual.
Okay. Okay. Let's create this ad hoc cycle.
So now you see that there's an edge from one the vertex from the top left to the top right, bottom right or something. So that creates So that
Huh?
creates a bounded region that is adjacent to each of those, and they are
Yes.
so
Yes.
and
Yes.
one of
Yes.
them is connected adjacent to two of them. So that increased by one exactly.
Hmm.
So
Hmm.
by that, I think I can claim that there will be one region adjacent to three bounded regions that corresponds to cycle in the dual.
You are correct, but we need to write it precise. So let's think. Huh. Mm, okay. So there are bounded faces. So if there is a cycle, there are bounded faces. Okay. So I should not write this. I should write what? There is a cycle. So that means that in face. So that means there is a bounded face which is adjacent to three bounded faces. So if this hold, we will verify this claim. More or less intuitively it is correct, but this should hold. So if there is a bounded face which is adjacent to three, if there is a bounded face f, I should say f. So then what will happen if this is a bounded face which is adjacent to three faces? Then one of the vertices corresponding to this bounded face will not be boundary to that one, right? What is going to happen basically? Because if these three are adjacent, so let's say one is this one, another one is this one, and if there is something which is adjacent, another bounded face which is adjacent to this one, then this vertex is not going to be boundary for the unbounded face, right?
Yes.
So that means there is a vertex which is not boundary to unbounded face, This will imply this is a contradiction. This is contradiction to outplanarity of the graph. This is contradiction to outplanarity of graph. So that means what holds? That means it holds that what we are trying to do. There can this is a tree. So vertices on bounded faces is a tree. So that means on dual the subgraph corresponding to vertices corresponding to bounded faces is tree. So now if it is tree, then you can argue, right? Then what? If it is a tree, then it has a vertex of degree 1, right?
Yes.
So what?
So that corresponds to in the planar graph vertex with degree 2.
How?
Because that's a vertex that is part of a region, so bounded region. So that can only happen if it has at least two edges coming out, right?
How?
Because
How you
it's
are
a bounded, you can't bound with only one edge.
it is one side of this. Okay, so there is a face. Okay, so there is a face which is adjacent to only one bounded face. This is saying only this much, right?
Yes.
The face is adjacent to only one bounded face.
So at least if we have one bounded region in the planar graph, that definitely means that you have degree 2 in that.
At how you are concluding this, I am still not clear. So suppose you are saying something that this is now this vertex. Okay, this is adjacent to only one bounded face. This, suppose these two are bounded ones. So if these two are adjacent, then how you are concluding then there is a vertex of degree 2, because I can increase this thing now, like this, something like that.
No. So I'm saying that when you have before this, the claim was that the claim we got that the thing we proved that is that we have the bounded regions as a tree, right? So that means that we at least we have one bounded region. Then
which is adjacent to only one bounded region. That is only saying that.
Yeah. So when we have at least one so the claim is that
okay. So you are claiming what thing and you are saying what? Let me write. Then it will be more clear. But it is correct what you are saying. It should be correct. I have another. I am thinking something else. But
yeah,
let's follow your.
I was saying as that if we have that the bounded regions in that wall are as a tree, then we have a leaf. So that leaf will correspond to a bounded region that is only adjacent to one of the bounded regions. So then at least one vertex will not be will have to be definitely be at it will have to look like a triangle or something, and one
okay. So let's suppose this is looking like this.
I'm not strictly putting that it must be a triangle, but I'm saying
no,
that
I understand. Yes.
Yeah, so then there will of them exist at least one vertex that has two edges in the sense that if it were not the case and it had even more edges coming out of
then
it,
then you need to argue it. If there is, suppose there is no such vertex, then there will be, you are saying, I am giving you case something like that, then you will say go on, trace this path of the tree. At some point this should be like a tree. Otherwise, if there is a cycle, then this will be some bounded phase.
Yeah.
But what is the problem if this is some bounded phase? Let's say something like this here. So what is the problem?
If it's as such that it keeps on adding another bounded phase, then it contradicts our initial claim that the corresponding vertex in the dual was one with as the leaf. No. if you keep on adding it, you have already chosen that as a
But
vertex.
this is not contradiction to that one, because that is only saying that that face corresponding to the leaf is adjacent to only one bounded face. This is not adjacent to this bounded face, right?
Yes, so the bounded face on the right, that is, if you say that is actually that's not what is the what I was trying to say is that the region corresponding to the leaf,
Hmm.
if it were such that suppose there were no degree vertices with degree 2, so that
Okay.
means either a loop occurred somewhere,
Okay.
or another region, bounded region started from there. So
Okay.
basically, in either case, so if a cycle,
But the second point is not correct. Now, another bounded region is not correct, because this can happen and that this is connected to by some edge to some other vertex, and there is some another bounded region connected to that vertex, right?
yes, so then you can the bounded, you already said that it was a bounded region, but if you say that the vertex that you pulled another bounded region from, then that's
Huh?
not a bounded region, no, that's just a boundary.
Huh? So what?
So so the your initial claim that it was a bounded region is not true, no?
Okay.
So it must be that you are talking about the one you drew at the end.
Okay. Let's write. But what you are saying, I feel that there is a loophole. Let's write. Okay. But your argument should go ahead. Okay. So we have to show that. So that means what we have concluded from above. This means that there is a vertex in dual graph corresponding to some bounded face which is of degree 1. This will imply that,
Oh, bounded
huh?
face of degree 1 means?
I am talking on dual basically. I should write it. There is a vertex is dual. There is a vertex in dual graph
Oh, yeah.
in dual
In
graph
dual, there is a vertex of degree 1.
corresponding to some bounded face of which is okay. I guess that is correct now. Which is of degree 1. Maybe that is language problem, but
Okay.
huh. So so that means that this bounded face f, let's say f, that means f is adjacent to one bounded face, at most one bounded face. So that means what you are saying now.
Uh, so, so the vertices that bound that region. So we are talking
Vertices
about that bound that
which
region.
bounds f,
Yes.
huh?
Among the vertices which bounds that region, among, yeah,
The
among,
vertices which bounds f,
yeah.
huh?
The claim is there exists at least one vertex with degree
Huh?
2. So,
There exists, huh?
uh,
A vertex with degree
yeah.
2. Huh?
So now assume the contrary, that this wasn't the case. So
If
that
this doesn't hold, so what?
so that means there is so that means all of the verti so that means all of the vertices, mm,
Huh?
are actually then again then again have another bounded region adjacent to them. So each,
Okay.
so let me try to say this neatly. Yeah, so your objection in the first point was that maybe it's not even a bounded edge, bounded region that is adjacent, just an
Hmm.
edge, right?
Huh?
Yeah, so you are saying that so okay, let's assume that it's not a bounded region, it's just an edge. So in that case, what is happening that say each of the Yeah, uh, each of the vertices has a have a single have a mm, single neighbor with degree
Hmm.
1,
Hmm.
and then maybe that neighbor has some other bounded regions
Yes,
with it.
yes, yes. That's what I'm saying. That's what my worry.
Okay, so in that case, here is something that I wanted to ask. In that case, do we say, so when we have that dual, do we
Hmm?
connect these two regions? We don't, right?
No, they are connected to that unbounded one by basically, not
Okay,
exactly that.
okay,
Huh.
okay. So yeah,
So what?
answer. Yeah. So if every one of them, okay. So yeah. So you have to find among all the leaves, I suppose. You have to then we have to add that there exists a leaf that is such that.
Yes, that will work. Now I got. So a single leaf it will not work.
Yeah,
Yes,
so you can choose an arbitrary leaf, I suppose.
yes,
Yeah,
yes.
you
Consider
have
the
to claim that
subgraph.
there will exist a leaf with this property.
Yes, that will be correct. So where we should improve this proof, there is a vertex which is not boundary to unbounded space.
So
This is
when
contrary.
we chose our vertex in the
Leaf.
dual graph,
So consider the subgraph corresponding to bounded space. If there is a cycle, so then this is this on dual subgraph
yeah, there is
corresponding
a
to bounded.
vertex in dual graph.
Uh, uh,
Okay, there exists a vertex among all leaves, I suppose, in the dual.
uh, uh. So there exists uh, a vertex of degree 1 among all vertices of degree 1 in dual graph corresponding to some bounded space F which is of degree uh, okay, okay, bounded space F bounded space, okay. So F among the vertices is bound self.
So then
Now
at the end we can
we need to
basically
erase this.
say
Yeah,
that if there is no such bounded face with the property are we
then
looking
it will
for,
work.
then that
It will
means
work.
that our original assumption that it was adjacent to at most one bounded edge is false, because
Yes,
then it
yes,
connect
yes,
together and create another bounded edge inside.
yes, yes. That's correct. So let's write this. Okay. So there exists a vertex of degree 1 among all vertices of degree 1 in dual graph corresponding to some bounded face F. Okay. So claim, uh, claim. I should write there is a leaf uh, uh, leaf such that it has uh, on its original graph in its graph original graph I should write is I'm coming to its original from dual on its original one the region it corresponds is bounded by a vertex of degree it moves to okay. If not, that means what? If not, that means uh, it
So
means if not
then
uh,
we get another bounded region that's adjacent to all of the
yes.
regions corresponding to the leaves.
So if not, that means there is another bounded region which is adjacent to that leaf, so that which is contradiction because that leaf has degree 1, which is contradiction since leaf has degree 1. So we are done. So this implies on outplanar graph, thus every outplanar graph has a vertex of degree at most 2. So yeah, this is more or less a sketch of the argument. So are you able to follow, or I guess you are, right?
Yes.
So this is more or less clear. So I also haven't tried this before. So this I haven't tried, but this may be easy. I don't know. So before this, I need something, I guess. So let's do this first. So let G be a K regular XY bipartite graph such that cardinality of X is cardinality of Y. Let then prove that has a matching that covers X. Has a matching that separates or covers X. Saturates, sorry, covers, saturates, whatever, X. So can you think something? G be a K regular graph. So K regular means each vertices have degree K, and this is XY bipartite graph, and both have same cardinality. You need to prove that G has a matching that covers X. So what is the immediate theorem coming in your mind basically? By you need to show that G has a matching that covers X. So that means what? We recalled initially, right? What theorem?
False.
Hall's theorem. So, but for Hall's theorem, we need to prove one thing, right now, to apply Hall's theorem. We need to prove that for every S subset of X,
Yeah,
neighborhood
the
of S
neighborhood, cardinality of the neighborhood
should
is
be
greater
bigger than
than the
this
set.
one. So how to prove this? What is this thing
Where
going
K,
to be? This is going to be what? This is bipartite, K regular bipartite graph. So this is going to be what?
so this is K,
This is going to be K
at
times
least K. So K times the number of vertices in S. So
cardinality
K
S.
times cardinals. Yeah,
Huh.
yeah, this is clear.
So this is K times cardinality. But what about if they are repeated? So they all are going to same vertex.
Uh,
If this will cause some problem or something? Yes, that should cause some problem,
so,
right?
what did you, can you repeat?
So I am saying that each vertex have degree K, na?
Yes,
So each, like all the arrows are going to be same vertices for one vertex, let's say.
all the, so,
Ye-
uh, all the arrows
This
are going
neighborhood,
to same vertex.
you are treating all that as a different, na? Neighborhood of S means all the vertices which are adjacent to S. But this is like this is giving on you only one vertices. If they all K, all these are same basically. All these are going to same only one vertices basically B1.
So, but
I know that will
that can't happen for all its degrees, no? You need at
for
least
that
as
that can't happen for
all its neighbors, no? Because so say suppose you have some vertices, same vertices, then you say
hmm,
that these AM vertices have the same neighbor in the other side, or the partite side, right? That is the kind of situation you are saying.
Yes.
But we have that each of the
Each point of y has a degree k, so there can be on at most k going to this. So yeah, this should be correct. Yes, this should be bigger than this thing basically at most. Sorry, what I'm saying, k times cardinality s divided by k, because on y each vertex can at most like k things can come to this basically, right?
yeah.
So this is like this thing should be at most bigger than. In fact, even this happens that all they are going to this thing will hold, and this is basically cardinality of s.
Yes.
So yes, so you can apply Hall's theorem, and that is direct, right?
Yeah.
So every G partite, so G K regular bipartite graph has this thing. It is clear, na?
Yes.
Do I need to write or?
Let's go to the next question.
Okay. So this is good problem. Now this will be used in this one. That's why I did this. So question. Uh, let r less than n, any r cross n Latin rectangle can be extended to r plus 1 cross n Latin square. So are you familiar with this Latin rectangle and Latin square thing?
No.
Okay, so let me define. So in R cross n matrix, corresponding and what I'm writing in an R cross n matrix, which is given by the entries 1 to up to n, and R cross n matrix consisting of the numbers 1, 2, so on n is called the R cross n Latin rectangle if the same never appears twice in any row or any column. So if r equals to n, and then it is called Latin square. That is called Latin square. So this is the definition. Basically, each row and each column uh, should have like if there is a one in one column, then there should not be one in that column again, and if there is some entry in this row, and that should not appear again.
Okay.
So example is like something you can see. Suppose you are working on 4 entries, 1, 2, 3, 4, then 2, 3, 4, 1. This is a 2 cross 4 matrix, and this is a Latin. You can see 1, 2, 2, 3, 3, 4, 4, 1, 1, 2, 3, 4, 2, 3, 4, 1. Right. This is an example of the R cross n. Only note this thing in this
So
definition.
we only consider each column separately,
Each
each
column
columns
separately
and
means,
rows separately.
yes, each column and row separately.
Okay.
In each column and each row there should be like in each row there should be nothing common. In each column there
Yeah,
should
yeah,
be nothing
yeah.
common. Yes. So note only this thing, that this n and these numbers are same basically. Yes. This columns and this up to 1 to up to n. So the question is this thing. I write question again, right? Yeah, this
Yeah.
is the question.
Yeah. So we extend to r plus 1.
I guess this seems to you obvious. This may seem to you obvious. Yes.
Extended to r plus what is 1?
1. I should write r plus 1. Where is pen? Yes. R plus 1.
So that would
It, will-
only be a Latin square if r plus 1 equals n, no?
hmm?
That would only be for r plus 1 is equal to n.
No.
Then Latin square said that you have to have.
Means we can inductively, basically, if you do it for r plus 1, then you can follow this inductive argument up to n. That is what this problem is saying.
Okay, okay. Where are
Try
you
to use
getting? How do you extend the? Where do you get the numbers from?
1 to up to n.
1 up to n. Okay.
Hmm.
Okay. And we have r less than. Oh, yeah. Yes. So basically, that says that uh, our r times n Latin rectangle is part of some n times n Latin square, right?
Hmm.
So
But how you will construct that n times n Latin square from this r plus 1 plus n? Can you construct some bipartite graph from this thing, and then you can go to your tools, Hall's theorem, and something which you have done previously?
okay, so Latin square is that no row and no column is same. Okay,
Hmm.
so uh, so no row and
Try to make this as a bipartite, some regular graph. Then you have, you can use your previous part, what I have done previously. Another hint, that each row has like each column has only how many entries? Each column has only r entries. So n minus r entries are not there. So how you can make it? You can try to make it as n minus r regular graph among what? Now you think, right? Now you have enough. Right? Each column has only r entries, so there is not n minus r entries are not there. And you want to include some entry among these n minus r entries there. That's how you will extend this to r plus 1.
okay. 1 second.
Hmm.
In the bipartite set, uh, uh, so we are expected to get a bipartite graph, right?
From this thing, given data, how you will do, and then use previous one and something prove that this is there is a matching. G has a matching that covers yeah, this previous one, right? This matching thing. Then extend it basically. Basically, what you need among these n minus r numbers, you want to assign one number to each column, right?
Among yes,
Because each column
yeah,
has only r entries, so you have n minus r remaining things. Among these n minus r things, you want to assign each something to each one, right?
yes. So okay. So basically,
So
we have a set with the so we have a
so
set with
here you have set of columns c1, c2, cn, n columns, and here you have 1, 2 up to n, right? This is bipartite graph. Up now, what is the edges you have to think? What is the edges I should make? C1 goes to which thing?
so
There is
uh,
an edge E from C1 to E, and edge from C1 to I. If I does not belong to C1, that's what I want, na? That's why
yes,
what I want to increase this order. So this is a what regular graph. So can you see this
n
is a
minus r
bipartite?
regular graph.
Yes, this is n minus r regular graph, and this is bipartite. So bipartite n minus r regular graph. So that means by previous one what? This is G has a matching that covers X, right? Hello.
Hello. Yes.
Yes. Can you hear me?
Can you repeat?
Yeah. So we have seen that this is bipartite plus n minus r regular graph, right?
Yes.
So that means by previous one, what we can say? This is a matching, right? By using
Yeah,
Gauss
yeah,
theorem, what?
yeah.
Yeah. So for each CI, we get some element which is not in CI. So that way we can exclude it to R plus 1 cross n Latin rectangle, right? This will give you R plus 1 cross n Latin rectangle, right?
Yes, yes.
So then do inductively up to n. So you will got done.
Okay. So,
So have you got on
so R plus one basically means adding another but
another row?
so then so what happens? So we add
Each
what
column
so
we have added one entry, right?
one element. Okay.
So that will increase the row, right?
Yes.
So we are done. Is it
Okay,
clear
okay.
or
So
I?
oh yes, I get. So it's already n minus r regular. So
Huh.
but this is bipartite, so I can make it n regular basically because
Yes, yes,
yeah, yeah, up to n regular. Yes.
yes.
Uh,
So it is clear now.
Yeah.
Should I write it?
Mhm. No.
Okay. So let's go ahead. Hmm. I should write go inductively till at. Hmm. So now next. So this is question. So that there exists a planar graph on n vertices with 3n minus 6 edges for all n bigger than equals 3. So can you show this? Can you give me some graph for which this holds?
Paragraph. Then what is this? Second part. Mhm.
Let's start with n equals 3. What is for n equals 3?
Uh, so for
Uh,
n is equal to 3 and n is equal to 4, it's the regular graphs on these vertices. So for
hmm.
5, it becomes less.
Hmm. Hmm. For what about 5?
Then 5, it's no longer the regular graph. We have less
Hmm. So
edges.
what?
So we
So
have
can you
9
think
edges
something
on
else?
the. So on 5 vertices, we have 1, 2, 3, 4, 5, 6, 7, 8. We want to show that there always exists with
Huh.
exactly this, right?
For each n, there exists a planar graph with 3n minus 6 edges. So let me give you for n equals to 5. So then you think.
Yeah, I mean, I got the graph.
Okay. So tell me.
So basically, draw the pentagon.
Okay. Draw the pentagon. So you have this thing and this thing. Let's say.
Yeah,
Huh.
connect the topmost to the bottom left outside. Okay, it's fine.
It's fine.
Same with the bottom right, topmost to bottom right.
Hmm.
Then connect the uh, top left to top right, and the same
Acha,
for the other side.
top left to top right. You said
Same. We do that too, I suppose.
this one.
Yeah, sure. How many we got? 1, 2, 3, 4, 5, 6, 7, 8. And then add another one from the top left to bottom right.
Top left
Sorry, not
to.
top left, but you can, but yeah. And that's not a correct edge, no? You already they are already adjacent. The last two you do.
Okay.
So the um, top left
Hmm.
to bottom right.
Okay. Why you are thinking in this way? I don't know. Okay.
Yeah. We
Huh.
have 9 edges.
So okay. Hmm. So, but this way you can't. How you will see this way you can extend?
I suppose an easier construction is there. So that's like
Ah, I
basically,
know something is here. Right. What you
yeah.
are given
So
is.
say let me say.
Hmm.
So basically, for n is equal to 6, let's draw
Huh.
this.
Huh.
Draw a vertex with degree 5. So spread it out around the vertex. A
Okay.
vertex with degree 5.
Oh,
Yeah.
vertex
So
with
5
degree 5.
leaves.
Okay.
Yeah.
Okay.
So 5 leaves come out of it.
Hmm.
Yeah, and then connect the boundary, make a boundary as we would follow.
Okay.
So this adds 10 edges, 5 inside,
Hmm.
5 outside.
Hmm.
Yeah, so the remaining two are basically we can see. So any connect we can connect two outside.
Okay. So what you are saying, you can think, but I think in this way. Basically, at each step you have to add how many edges? Basically, n plus one. You have to add how many edges? So basically, you have to add three many edges at each time, right? So I will do in this way basically. Instead of if I were in your place, I will think. I thought in this way, like when I first saw this problem. Each point I will go to add basically one edge to top one. 1 is to this one, 1 is to this one, 1 is to this one, right? This is going to be regular. Then I going to increase a vertex. I have to increase 3 edges. I will increase 1 edge here, 1 edge here, 1 edge here. In this way I will do. This is the most obvious way to think. I don't know why you are thinking. Okay, fine. So do you understand this? How I'm saying?
Yes.
So this seems more obvious, now.
Yeah, I think this is basically same to the last construction. You are adding one inside, one outside, and a new.
Huh. So you are saying what construction? You are giving me a vertex. Then you are saying,
So you
okay, do it.
whenever you add a vertex here, so basically
Hmm.
add one to the center one,
Hmm.
and then you and then one another additional vertex edge gets added to the neighbor, and the one
Okay.
that covers it. Three
Okay.
edges.
Fine. Okay. Anyway, you have got what I am saying, and you have
Yeah,
the planar graph for each end, right?
yeah.
So what is that means to so I am not writing. So basically apply, do this inductively. This figure is making, so I add a vertex and join it to 3 vertices of triangle and proceed it for each end and inductively. So what about bipartite graph? So can you find something? So question is this thing. So what I should say? What is bound for bipartite graph? 2n minus
Four.
4. So there exists a bipart for each n. There exists a bipartite graph with 2n minus 4 vertices. Can you see?
For
For
each
each n,
end,
can
there is.
uh, this is easy, more easy than previous one.
Oh, uh, yes,
Hmm.
yes. I think I can.
How?
So for each n holds for greater than two, greater than or equal to, right?
Okay, yes, greater than equals to.
Yeah, you yeah, wait. Okay, so we are talking about planar, right? Not just any,
Bipartite. Bipartite.
just bipartite.
Yes. At planar also. Hmm. Otherwise you can get easy.
Yeah, yeah. Yes. So whenever we add another vertex, uh, uh, that
Hmm.
increases the. I'm missing something actually, I think.
Okay. Think about this thing for each n. How many edges this have?
Just two and four. No,
Hmm?
one second. So this is at most 2n minus 4 edges. Then we have that 2n minus 4.
So basically you can think in this way, na? Suppose you have n vertices and one vertex is here, one vertex is here. Each one is so you have how many edges basically? You have n vertices,
exactly 2n minus, because
2n edges basically. You have
2n is there, yeah. But
so मतलब 2 times 2n
the
edges is there, and then vertices is basically n plus 2. Vertices is n plus 2. So
yeah,
what I'm saying
is that because we have the in the middle portion n minus 2 vertices, and each of them are getting 2 edges,
so
we have 2n minus 2.
so that means we have 2
n
times
minus 2 times
cardinality, and this should be cardinality v there.
yeah.
So this is what.
So this is 2n minus 4.
Huh.
So you should put a bracket. Yeah.
Yes, this should be correct. Yeah. I should write 2 times cardinality v minus 2 in this way, right? Yeah. Clear, na?
Yeah.
So yes, these bound are strict. You cannot make something lesser than that in general. So we have proved this every planar graph has a vertex of degree at most 5, na? In this lecture, have we done?
5? No, I think. Did you
I
do
guess we're
5?
done here. We've done this one. Yeah, this one.
Oh,
every
yeah.
planar, we have done this. So yeah, now this will be used in this problem. This is the problem where we need to 4 colors, but this we are saying for 5. We will prove this for 5. Question: G planar graph, you can assume connected as well. Then chi is less than equals to 5. Basically, in fact, you know chi is 4. There is a theorem which he mentioned in class, which is slightly hard to prove, but we will prove chi equals to 5 at least. For G, Ig already right. G is planar graph. Yes. So try to use that G has a vertex of degree at most 5, which I proved. How will you proceed?
G has vertex and degree at most.
Think inductively. Base case is done now. If there is only one vertex, obviously that is true. So assume for n and use the previous fact. Remove that vertex, some vertex, then you will get to n vertex. Their hypothesis is true. Then what you can conclude? Think in this way.
Are you saying to do this needs dual?
No, I'm not saying that, because dual will not help here. Because you need to color the vertices. How dual is going to help? Because
Oh
in
yes,
dual
color
you
vertices. Yeah, vertex color.
so dual will not preserve this vertices data. No?
Oh yes. So in the previous section we proved that the degree is at most 5, right?
There is a vertex of degree at most 5. Yes. एक वर्टेक्स होगा जिसका डिग्री 5 होगा. बस होगा.
Ig is okay. So for arbitrary graphs, yeah. So for arbitrary, if you take any graph, then of course you will need at least 5 colors in the general case, because you have 5 degree 5, then you can in that case we will definitely need 5. You can distinctly color them, each of the vertices. That will create the graph to be properly colored. Yeah.
Hmm. But you
So
need at least 6 by that argument. Now, basically, you have each a vertex of degree 5, at most 5. Other vertices can have degree larger as well.
yeah,
But
yeah,
this vertex,
yeah. We are seeing at least this much colors, right?
hmm. So there is 1, 2, 3, 4, 5. So each one, if you color each one with different one, then there will be one needed for center. So you will need 6. So how you will proceed?
So this is the maximum case. So
Hmm?
this does not violate it, right? Because so we will have the degree at most five. So there will be a vertex with degree at least 5. No,
At most 5.
at most 5. Yeah.
Hmm.
So in that case, we need 6 colors. That is fine, because if you have
We don't need
any.
6. I am saying we can color it with 5.
Okay, so you have planar graph. Yeah.
Hmm.
So you have planar.
But now I am missing something. I
Can you
indeed
go
doubt.
up back where we proved this, the 5 part? Let me redo the steps.
Yes, this one.
Prove that every planar graph is subordinate. So yeah.
If each vertex have degree greater than 6, then this thing doesn't hold. This is planar. So how to do this? Okay. Mhm. Yeah, this is done now. This is easy. Yeah. Induction. Go to induction. Go with induction. So base case is done now. For n equals to cardinality v equals to 1. Done. So assume it is true up to n vertices to prove it for n plus 1. Right? We need to prove it for n plus 1.
Yes.
So we know there is a vertex of degree 5 at most. We know there is a vertex in G of degree at most 5. So consider some other graph, let's say G star, which is G minus this vertex degree at most 5, say V. So G minus this vertex V, then G star, we know by hypothesis chi of G star is less than equals 5. So only need to check about V, right? Up to this is it clear about neighborhoods of V basically. Check about neighborhoods of V, right?
Can
Hello.
you repeat?
Huh. So I am saying that I start with induction. Base case is obvious. So assume this is true up to n vertices. Then you need to prove it for n plus 1. So I am saying that so for n it is true and we need to prove it for n plus 1. Suppose
Yeah.
G is a graph with n plus 1 vertices. Remove one vertices which correspond to degree 5 at most.
Okay. So yeah. So G. Oh, okay. So G is with n plus one. Okay. Okay.
Okay.
So yeah, for J star, it's the hypothesis.
Huh.
Then yeah. So we need
So
to only check for B. Okay. Okay.
neighborhoods of V. So now what is the argument is this thing. What you are trying to say that is correct basically. What way you are thinking. So there is a vertex which have degree 5 now. So each one should be colored different, but how to change color in this one? This is, let's say this is this color, this is something, this color, all are going to be same. So so I don't know, there is only three color option. So fine. So we need to give it how much? Five colors. So suppose these pipes are different colors. So suppose this is red, this is blue, this is green, this is yellow, and this is something like uh, brown. So we have five color and we need to color the center one with some color. But this cannot be colored something with same. So what we do, so there will be some connected to this one, right?
Yes.
So if not, if there is nothing connected to this one, then what will happen? You can
Uh,
color these two as a same color.
Same
So then you
colors.
can
Yeah.
color, yeah. So if there is connected to something, this one, some cycle to this one and some cycle to, let's say, this one, what you can do, you can swipe the colors of this trees on this one basically. If this, so basically, suppose this is red, this is yellow, this is, you can color this tree in this way, right? This is
Yeah.
red,
Alternately.
this is, yeah, yellow. Then you can swipe this color basically.
Yeah. Yeah.
So then these two will have same color.
Yes.
Red and these two vertices will have same color. But you will have a doubt, what if there is a cycle? So what is the meaning of swiping here, right? Then this will not work, you are saying. But what is the problem, that then the same choice, this vertices and this will work, because then they cannot be cycle between these two and these two. This, let's say this is W1 and this is W2. So there cannot be any cycle between W1 and W2 because this is a planar graph, so they cannot intersect, right?
Yeah. Yeah.
So
Yeah.
you can do same thing. There is some tree, so you just swipe it out basically, colors, and you can make them same color, right?
Yes.
So this way it will work. So let me write. So what we have done, so we have at most five neighbors. Case one, if there is nothing connected to neighbors of V, then color each one the same color and be different. With same color and be different, and V different color. We are done. We are done. Case two, case two. If there is a tree, but if there is a tree between, let's say, name these vertices W1, W2, W3, W4, W5. If there is a tree attached to some vertex, say W1, but not connected to some other, say W2, then color W1 and W2 with same, we are done. We are done. Case 3, we have to write similar cases. If there is a cycle between adjacent ones, then there will be a remaining vertex which is not which is if which is not connected to anyone else, if not connected to any other, color it with same, we are done. Otherwise swipe the color and well done. Case 4, if there is a cycle between alternate vertices, then say W1 and W3, then join, then color W2 and W4 same, since they cannot join. So we are done. So in similar way, you are done for all cases. Done for all cases. So with this, I will stop here. If you have any doubt, you can ask. Sorry, stop recording. There is recording. This one.